Take it up from there. All right, so welcome and hope everyone is okay. Welcome to the Mr. X free Zoom lesson. Today we're going to be doing electric circuits. That's what we're going to be doing today. But I'll start off with this. I'm going to share the screen quickly here so that everyone can see what's going on. All right, so first things first, probably one of the most important things happening in the next coming couple of weeks. I'm going to be holding a massive revision program for mathematics and physical science. This will be an 8-hour-a-day face-to-face revision program where I will be teaching and revising past exam papers, tackling high flyer questions, focusing on those questions with a lot of marks, challenging topics, giving you exam tips, teaching you about time management in an exam as well as intense assessment and feedback so that we can be adequately prepared for our final examination. This particular revision program will occur this particular November, in the beginning of November, 2, 3, 4 November. That will be the mathematics, and then 9, 10, 11 November, every single one of those days on a face-to-face. It will be happening in Braamfontein. If you're interested in it, you can book your space. But for now, I am busy taking bookings, yes, and it's 1,200 rands per subject. So if you're interested in it, DM me, check my Instagram page, check my Facebook page, and more importantly, check my YouTube page as well. This particular video for today will be uploaded on YouTube so you guys can get what you need to get. We're doing something that's very challenging to most of you, and that particular topic is electric circuits. So here's what we're going to do. I'm going to beam a question, then I'm going to do it. If you have any question whatsoever as I am teaching, let me know by raising up your hand through the platform. I should be able to see you when you raise up your hand. Then I will unmute you. All of you are totally muted, right? So I will unmute you and we take it up from there. We begin with no time wasting. I must acknowledge where I get the paper from, 2013 March paper 1, and it's question number 9. You can just write that one down on your books. Get your book, your pen, your papers, everything, pencils, and your calculator. Let's get busy. Let's start learning. 2013 March, paper 1, question number 9. It reads as follows. The circuit represented below is used to investigate the relationship between the current passing through and the potential difference across resistor P. So you've got your circuit right there. And so there are components on this particular circuit. And I want us to discuss those components as we see them. So what I look at is the switch right here. So that's called the switch. I'm looking at a resistor P. I'm looking at the voltmeter connected across the resistor P. So it must be clear. The voltmeter is always connected across. But in contrast, the ammeter, which measures current, is connected along a circuit or in series. You can say the voltmeter is connected in parallel and the ammeter is connected almost always in series. Then you've got here the variable resistor, or you can call that the rheostat. That's your basic setup. I see that. It is a graph. It says the results obtained are used to draw the graph below. Okay, graph of current versus potential difference. I'm looking at that. Current happens to be on the y-axis. Potential difference happens to be on the x-axis. The graph is a straight line graph and it passes through the origin, or rather it has the coordinates of 0, 0. So it's important then to interpret the question properly. 9,11. Write down the independent variable. 9,11, write down the independent variable. Now, in a typical graph, any graph for that matter, this would be your x-axis, this would be your y-axis. The independent variable is always found on the x-axis all the time. It's the independent variable. So this is where you'd find your independent variable right here on the x-axis. So you can see that the independent variable in this case is potential difference. So for 9,11, it's potential difference independent. And just by the same extension, the dependent variable is found on the y-axis. Dependent. If you did maths, the independent, which is x-axis, would be your input value. And your dependent, which is the y-axis, would be your output value. So 9,11, definitely it's going to be potential difference. Now we go to 9,12. Write down the variable that must be controlled. Because we're doing electric circuits, this graph is a graph of potential difference versus current. It's a straight line graph. It's a graph from the experiment of Ohm's law. And in Ohm's law experiment, the variable that must be kept constant throughout is temperature. And this is because temperature will affect the readings or affect the resistance. Remember, when you're stating Ohm's law, you're going to state it as the potential difference across a resistor and the current through it are directly proportional at constant temperature. That's the key phrase, at constant temperature, suggesting that the temperature must be controlled. So 9,11, definitely the temperature must be controlled. All right, 9,13, it goes further. 9,13, be writing these answers on the side and the questions where I took them from. 2013 March, paper 1, and it's question number 9. 9,13, write down the conclusion that can be drawn or obtained from the graph. Well, basically, because it's a straight line graph that shows the relationship between potential difference and current. So then when you're concluding, you conclude by stating Ohm's law. Basically, the conclusion of this graph, when we interpret the results and draw this graph, the conclusion is Ohm's law. And what does it say? 9,13, I'm giving you the answer. The current passing through a resistor, you can write that one down. The current passing through a resistor is directly proportional. Current passing through a resistor is directly proportional to the potential difference across that resistor, directly proportional to the potential difference across that resistor at constant temperature. Directly proportional to the potential difference across that particular resistor at constant temperature. That's what you have right there, at constant temperature. All right, beautiful. So I'm good to go. Let me try 9,14. Now, 9,14 says, using the gradient of the graph, calculate the resistance of P. Using the gradient of the graph, calculate the resistance of resistor P. Okay, let me help you out understand this. Now, in a typical graph of current and voltage here, like the one that I'm trying to portray here, let me teach you this. So if you have current on the x-axis and voltage on the y-axis like this, and your graph will be a straight line graph, then if you calculate the gradient of that graph, and let's keep in mind what gradient is. Gradient is change in y values over change in x values, which for me will be change in voltage over change in current. When you have a graph like this, where current is x-axis, voltage is y-axis, straight line graph, then your gradient, which eventually is voltage divided by current, that gradient would be the resistance of that particular graph. So in other words, when you think about the formula for resistance, it's voltage over current. That's the formula for resistance. Now, in this graph particularly, the gradient will be voltage, I see that, divided by current, I see that, that's resistance. That's if you're given a graph like this. But look at the one that we have on our question. It is not like that. In fact, the one that we have on our question, what does it have? Try to draw a straight line here. Then the one that we have on our question, what does it have? It has potential difference on the x-axis and current on the y-axis, and still it's a straight line graph. If you calculate the gradient of this graph, you will get change in y values, which is current, over change in x values, which is voltage. And this gradient is not resistance, because resistance, as I put it across, is equal to change in the voltage over change in the current, or you can say V over I. But my gradient here gives me I over V. And the question says, using the gradient of the graph, calculate the resistance of resistor P. Calculate that resistance. Okay, let's break some physics down here. When I calculate this gradient, I'll get I over V. But I'm looking for resistance, which is V over I. So mathematically then, we can conclude that if we're using this particular gradient, which is what we have, then the resistance will be the reciprocal of your gradient. Resistance R will be the reciprocal 1 over m of your particular gradient. So let's get the gradient, then 1 over would be my resistance, because 1 over this particular gradient will give me V over I. Let's do some math. Right, I'm going to have my coordinates, and I'm going to pick them up from here. I'll pick this one here, which is 0, 0. Okay, that's always easy. Then let me pick another one. Let me try the one where x is 2. I see that x is 2, and then there's my y value somewhere here. When I do my maths properly, x is 2, and y is actually 0.74. So these are my coordinates. I'm looking for the gradient. Remember, you can only find gradient between 2 points. Fine. Now the gradient then becomes y2 minus y1, 0.74 minus 0 over x2 minus x1, 2 minus 0. That gives me 0.37. That's the gradient. But I'm looking for the resistance, so goes my question. So let's bring it this side. I'm looking for the resistance. Resistance will be 1 over the gradient, which is like 1 over 0.37. And at the end of the day, your answer becomes 2.7 ohms. That's your answer. The key again is noting what type of graph you have. Is it current versus voltage? Yes. Get the gradient. 1 over will give you resistance. If it was the other way around, where it's voltage on the y-axis and current on the x-axis, then just getting the gradient alone would be enough to get your resistance. This is your answer. Please write this one down. So that's R is equal to 1 over m. If you have any questions whatsoever, guys, you can always lift up your hand, and then I will be able to pull through for you from that perspective. I want us to move on to another question, or more of this particular question. I'm going to start off from something very small, understandable, then I pick it up and go a notch higher on more challenging questions. All right, Litavo, you raised your hand, and I'm hoping that Litavo is here. All right, but let me just say, Litavo there, I'm going to ask you to unmute you. Go ahead. You've been unmuted. Okay, let me try that again. Litavo Delron, he or she, go ahead, please.
Yes, sir.
Yes.
Sir.
I can hear you.
Hi. You
Yes,
can hear me?
We can. Yes. You can ask your question.
Okay. I think the last question, 9.1.4.
Yes.
Yeah, I didn't get it well because my Wi-Fi is giving me some.
Okay, I think it's still giving you a bit of a problem. Your Wi-Fi can hardly hear you. All right, but I'll try to explain it again. Let me just mute you in the meantime, so that I can pull through quite well there. All right. I was saying to you guys, when it comes to the issues to do with resistance and you're given a graph, the key for me is understanding that the type of graph that you're given will determine how you're going to be able to deal with your gradient. If your graph is strictly y-axis voltage, x-axis current, then the gradient would definitely be the resistance. But if it's this type of graph like the one that we're having right now, and you're having current as the y-axis and voltage as the x-axis, then it means, therefore, if you are able to get that gradient, and I'm here for the gradient here, I'm able to get it. It will be change in y values, current, over change in x values, voltage. Now, the reciprocal, 1 over m, the reciprocal of that gradient will eventually become the resistance. And basically speaking, this is exactly what I've just done on this particular board. So basically, that's what your answer looks like. Allow me to move on to the next thing here, or the next question. All right, here we go. 9,2. Gets interesting on 9,2. Right, 9,2 says the following, right? I'm just going to make sure that I pull through on 9,2. In the circuit represented below, a battery of EMF 30 volts, please note these important things. 30 volts, all right, and an unknown internal resistance R, I see that, are connected to resistors as shown, and it says ignore the resistance of the connecting wires as well as the ammeter and the connecting wires. Fine. Now, it says then further, the current passing through the 10 ohm resistor. So there's my resistor, 10 ohm is 0,6. I see that, I hear that. That's the current passing through the 10 ohm resistor, 0,6. Then it says, calculate the effective resistance of the two resistors in parallel. Two resistors in parallel. All right, let me break it down. If you got two resistors in parallel, there's always an easy way of calculating their effective equivalent resistance. So the word that they used here is equivalent, but I want you to know that you can also use the word, or can also be applicable to use the word total resistance or effective resistance. So equivalent, total, effective mean the same thing. So you're looking for the total resistance of the resistors in parallel. There's an easy way, right? We normally know this one that says 1 over R total is equal to 1 over R1 plus 1 over R2. This is correct. You can use that method. But I prefer that when you got two resistors in parallel, and you want to calculate their total resistance, the total resistance would be product over sum, or you can call it P over S, product. It will give you the same answer like this method that you have right there. Product, that gives me 6 multiplied by 10, sum, that gives me 6 plus 10. So your total resistance in parallel at the end of the day becomes 3,75 ohms. PS, product over sum. But this particular PS method that I'm using is only applicable when you got two resistors in parallel. 2. If you got 3, now you need to use that other one, this one here, add further, 1 plus R3 and all that. Guys, don't forget that when you use this first method here, and let's say you get 1 over RT total after putting your numbers for the resistors, let's say you get it as 5 over 16. Notice that the RT must always be 16 over 5. So don't forget to invert as you prepare for the final exam, if you're going to use that method, right? So please remember that the PS only works when you got only two resistors in parallel. That's fine. This I am taking out. It's gone, going. I'm ready. Calculate the current through the 8 ohm resistor. That's the question, and it's 4 marks. Calculate the current through the 8 ohm resistor. All right, let me make it clear for everyone. If you look at the 8 ohm resistor, the current passes through, let's say it's passing through this way, all right? Now, this current would have come from the 6 ohm as well as the 10 ohm, and the current from 6 and 10 joined together to pass through the 8 ohm resistor. That's what they would have done, right? Beautiful. And again, I want to make it clear that the current also passing through the 5 ohm resistor gets divided between the 6 and the 10 resistors in parallel. So hence you call resistors in parallel current dividers, because they divide the current. So current passes through the 6, current passes through the 10, and joins together to pass through the 8. So I'm looking for the current in the 8 ohm resistor. If I'm able to calculate the current passing through the 6 ohm, okay, the current passing through the 10 ohm, okay, and add them together, then that is the total current passing through the 8 ohm, and by extension, also passing through the 5 ohm. Listen to me carefully. So all I need to do here in this context is to be able to understand that current that is passing through the 8 ohm resistor, which I'm looking for, is the current passing through the 6 ohm resistor plus the current passing through the 10 ohm resistor. So the current passing through here and through here added together will give you the current passing through the 8 ohm resistor. Fine. Now, what do I know about resistors in parallel? I know that they have the same voltage. I know. So the voltage in the 6 ohm resistor, the voltage in the 10 ohm resistor will be the same. What do I know? I know the current in the 10 ohm resistor, 0.6. I know the resistance of the 10 ohm resistor. I can find its voltage. Let's do some math. So the voltage in the 10 ohm resistor will be equal to the current through it multiplied by its resistance. I have 0.6 for my current. Resistance is 10. My answer becomes 6 volts. So the voltage in the 10 ohm resistor is 6. But because they're connected in parallel, the voltage in the 10 ohm and the voltage in the 6 ohm are the same. So in essence then, voltage of the 10 ohm, all right, voltage of the 6 ohm, okay, are the same, 6 volts. So now the voltage in the 6 ohm, 6 volts. The voltage in the 10 ohm, 6 volts. Now I can find the current passing through the 6 ohm. Why? Because now I have its voltage and its resistance as well. So then the current passing through the 6 ohm resistor is always voltage over resistance. You must always remember these formulas. Okay, voltage 6, resistance 6, current in the 6 ohm 1 amp. But what am I looking for? I'm looking for the current in the 8 ohm resistor. It's going to be the current in the 6 ohm, which is 1 amp, and then the current in the 10 ohm, which we now know as 0.6. At the end of the day, the current in the 8 ohm resistor will be 1.6 amps. You use this idea, you must know pretty much everything to do with series arrangement, parallel arrangement. So all these things you must know, and this particular lesson is designed to help us to remember, to help us to know how to use these things when we're given a typical question. That's 1.6 amps. I'm going to 9.23 very quickly on that one. All right, hoping that everyone is understanding as we're pulling through. 9.23. I want to take this out. I want to go to 9.23. All right. It's important, and not just in this topic, it's important in every topic that when you are given a question, you choose the equation appropriate to that particular question. So your choice of the equation must be contextual to the question itself. What is the question asking? What do I have? And then you use what you have, what you're being asked, to pick the appropriate equation. And it must be clear also to say that there are many ways of doing these particular answers, and I'm just going to concentrate on one method because we need to cover quite a lot. I'm on 9,23. Calculate the internal resistance of the battery for marks. Internal resistance is given by the small letter r. Okay. EMF I'm given is equal to I. I'm picking an equation, R plus small letter r. That's what EMF is equal to. Fine. Now, big letter R always stands for the total resistance in this particular circuit. That's what big letter R stands for. So if I look at this clearly, the total resistance for this parallel arrangement, we found it as 3,75 ohms. That was in the previous question, or rather in question 9,21. Now, once you've got the 3,75, it's as good as if you took the 6 ohm and the 10 ohm and you combined them together to give you 3,75. In other words, what 3,75 does on its own in series is what 6 and 10 ohms do in parallel. So you've combined the 6 and the 10 into one thing, effectively 3,75. This 3,75 will be in series with the 8, in series with the 5. So then the total resistance in the circuit R is 3,75. I see that, plus the 8 ohm plus the 5 ohm, and the total then becomes 16,75 ohms. Fine. I'm looking for small letter r. EMF is 30. This we were told. I, the total current in the circuit, is 1,6. Is the one that we calculated in the 8 ohm resistor, because the current passing through the 8 ohm resistor is undivided. It is the total current in the circuit. It's the same one that will pass through the 5 ohm resistor, undivided. Fine. So I've got 1,6. I'm doing some maths. 16,75 here plus R. Open up the brackets. You eventually have 26,8. 1,6 times that plus 1,6 R. There's my 30. Now I've got 3,2 when I take out this 26 to the other side, and then 1,6 R. Small letter r will be 2 ohms at the end of the day. That's your internal resistance of the circuit. Fine. Let's try and move on to another one. Somebody raised their hand. I want to make sure that I attend to them. So I'm going to unmute you. Try to make sure that you're not in a noisy place. That's always easier. Go ahead.
Morning, sir.
Morning. Hi.
So I wanted to ask, I didn't really understand how you got the 3,75.
Okay, the 3,75, I got it in 9,21. That was question 9,21. Remember, in 9,21, all I was doing in this case was making sure that I get the effective resistance of the two resistors in parallel, which is the 6 and the 10. The method that I used was PS, product over sum. So I said the product 6 times 10 divided by the sum 6 plus 10. That's how I got the 3,75. And this big letter R again is the total resistance in the circuit. So I must include the effective resistance of the parallel 3,75, which will be in series with 8, in series with 5. Hence I get 16,75. So that's how I got the 3,75 by adding the resistors in parallel. All right, I'm going to take this out now, and I want to move on to my next one. Somebody's got a hand. I'm going to unmute you. Go ahead.
Hello, sir.
Hi.
So I wanted to ask, since the voltage does not add in parallel, does the ammeter add or not?
So I think you're asking, since the voltage is the same in parallel, does the ammeter add, or rather is by ammeter, I think you're talking about the current. Is the current
Yes.
different? Yes, the current is different. And it makes sense this way. Let me clarify. Let me take this out. It makes sense this way. In a typical parallel circuit, the current between two resistors of different resistances cannot be the same. In a parallel circuit, listen, the current between two resistors of different resistances cannot be the same. Now, if I look at the 6 ohm and the 10 ohm, current is always inversely proportional to resistance. In other words, my expectation is that if the resistance is high, then the current is small. And parallel resistors are current dividers. In this question, the current here was 1 amp and the current here was 0.6 amps. Notice, the bigger the resistance, 10. The smaller the current, 0.6. The smaller the resistance, 6. The bigger the current, 1. And so the currents cannot be the same because they are divided according to the resistances. More current will move through the resistor, which is less, and less current will move through the biggest resistor. So yes, they will be divided in that context. All right, beautiful. Let me try and move on to something else as well. Here's another question that we can try. This one is from the 2015 Limpopo paper, right? That one there. And it's paper 1, question 8. All right, I'm trying to pull through on this perspective, making sure that everyone understands. I'm ready. In the circuit represented below, okay, the battery has an EMF of 10 volts and an unknown internal resistance R. Voltmeter V1, I see V1, is connected, as you can see, across the battery, and voltmeter V2 is connected across the open switch. So I see all of that, and that's fine by me. And it says here, ignore the resistance of the ammeter and the connecting wires. So there's my diagram. We begin. 8,1. Switch S is open. Will the readings on V1 and V2 be the same? Provide a reason for your answer. Will they be the same? When switch S is open, provide a reason for your answer. Let me explain. All right, let me explain this quickly. I'm trying to move my system here so that I have got a smaller part of this. All right, let me try and explain there. Okay, now if you opened switch S, current is not moving through the circuit at all. It is not moving. So there is 0 current when switch S is open. The voltmeter reading V1 across the battery should effectively read 10 volts. Because if you think about EMF, colloquially speaking, EMF is the voltage across the battery when the switch is open. So I'm expecting V1 to have 10 volts when the switch is open. No current is passing through. Fine. At the same manner, I'm expecting V2, where the switch is open, still to record 10 volts. Effectively, here's the key. Effectively, because there is no current flowing in the circuit, any part of this particular circuit will record a voltage, which is the same as the one recorded by the battery when the switch is open. So when switch S is open, the readings on V1 across the battery, 10 volts, and V2 across the switch, which is open, will read the same. Because effectively, there is no current. It's as if V2 is effectively across the battery. So your answer for 8,1, when the switch is open, is to understand current as 0. And because current is 0, the voltage through the switch, the voltage that is measured across the battery will ultimately be the same. And that's a very important thing to keep remembering. This only happens when the switch is open, when current is 0 in this case. So I would write the following as an answer. Yes, because they said, will they be the same? So my answer is yes. Then here's how I would explain it. I would say there is no current in the circuit, and effectively, there's no current in the circuit, and effectively, V2 is across the battery. It's as if what V2 is measuring or has is what is V1 also having across the battery. So yes, that would be my answer. There's no current in the circuit, and effectively V2 is across the battery. That's my question right there, 8,1. Let's try 8,2 quickly. When switch S is closed, so now here it's happening now. Things are happening. Switch S is closed. The reading on voltmeter V1 drops to 7,5. Makes sense. I need to explain this to you. If you close a switch in an electric circuit, the reading on the voltmeter across the battery will drop due to internal resistance. So we must understand that 10 volts is what the EMF is. But because there was a closure of the switch, then internal resistance lost volts. Voltage or volts are lost because of the internal resistance of the battery. So you had 10 when the switch was open, close it, now you've got 7,5 volts. Understand that this 7,5 volts, when the switch is closed, right, is the voltage that is given to the resistors that you're looking at, the 6 ohm, the R, as well as the 1 ohm. I usually call them children. So imagine when you close the switch, the mother is your 7,5. This mother has 3 children. 2 of them are twins in parallel, and bigger brother, the 1 ohm. So that 7,5 volts, when the switch is closed, is the one that eventually is shared amongst the family members, twins and the bigger brother. Now, listen to my English. I did not say shared equally. I said shared. That's what I said. So the 7,5 will eventually be shared amongst this particular family members, 6 ohm and R, as well as the 1 ohm resistor. Good. Let me go for 8,21. What is the reading on voltmeter V2? Now that the switch is closed, the switch does not use electrical energy. So eventually, because the switch is closed, the voltmeter reading on V2 becomes equal to 0 volts. Because it doesn't use any electrical energy, current is now passing through, current is no longer 0, and so the V2 is now 0 volts. So 8,21, the answer is 0 volts. Let's go to what is big, 7 marks, that's 8,22. Here we go. If the reading on the ammeter is 2,5 amps, so there it is, 2,5 amps. That's the reading on the ammeter. The question then says, calculate the value of R, and that's 7 marks. All right, let's discuss. When the ammeter reading, or in the ammeter right there is 2,5 amps. Fine. There's 2,5 amps, and by the way, when you're drawing the direction of current, it's always from positive terminal to negative direction of current. So the current is moving here, conventional current. There the current passes through the closed switch, gets here, current gets divided. Some of it will go through the 6 ohm resistor, and then some of it will go through R, which I don't know. So current passes through the 6 ohm, I see that. Current passes through R, I see that as well. It goes all the way here and passes through the to the resistor 1 ohm. It's important to understand that this 2,5 amps is divided between the resistors in parallel. But when it passes through the 1 ohm resistor, it's not divided, suggesting to me that the current passing through the 1 ohm resistor is 2,5 amps undivided. So here's logic. Current passes through 1 ohm, rather 1 ohm, undivided, goes through the ammeter, undivided, gets divided between the twins, comes back together as one wall, undivided through the 1 ohm, divided through the twins. So because I know the current in the 1 ohm resistor, then I can find its voltage. Because mathematically speaking, my voltage in the 1 ohm resistor should be equal to current multiplied by resistance. Current 2,5, resistance 1. So the voltage there is 2,5 volts. That's the voltage in the 1 ohm resistor, 2,5 volts. But what did I say? I said the mother, when the switch is closed, gives us 7,5 volts. That's why I said it drops to 7,5. Now there are 3 children. The bigger brother already has 2,5. Well, 7,5 is the mother, 2,5 bigger brother has. So the twins must have 5 volts. Okay, what am I saying? If the bigger brother has 2,5 and the mother is giving 7,5, then the twins must have 5. In other words, I can safely say the voltage external that's in the battery is equal to the voltage in the parallel circuit plus the voltage in the bigger brother, which is the 1 ohm. 7,5 right there is equal to voltage parallel, which is equal to 2, which I don't know, voltage parallel. I know the bigger brother is 2,5. So voltage in the bigger brother will become 5 volts. So now I know the voltage in the bigger brother. But let's be clear. Since I know the voltage in the bigger brother, I remember that the voltage in the parallel circuit is always going to be equal. In other words, the voltage in the 6 ohm and the voltage in R is equal. So therefore, since now I know the voltage in the 6 ohm, and I'm just going to write this as a statement, and the voltage in R, they should be the same as the voltage in the parallel circuit. Why are they the same? They are the same because they are connected in parallel. You got to get this right. Voltage in a parallel arrangement is the same. What 6 ohm has as voltage, what R has as voltage, what both of them have combined as voltage is the same. So the voltage in a parallel circuit or in a parallel arrangement is the same. So now I've found the voltage pretty much in the 6 ohm, in the R, and in their combination. And I'm looking for R. So let's do some physics. So because I got the voltage in the 6 ohm, I can find the current in the 6 ohm. I can. Because in the 6 ohm, I've got its voltage and I've got its resistance. So I can find the current. So what is the voltage? 5. 5 volts right there. What is its resistance? 6. So what should be the current? 0,83 amps. So I'm good on that one. Fine. So the current passing through here is now 0,83 amps. Fine. But what is the total current of the circuit? 2,5. Okay. That 2,5 is divided between the 6 ohm and R. And what goes through the 6 ohm? 0,83. I'm getting to my 7 marks. So in essence then, I would say to myself now, I would say, okay, the current, right, total will be the current passing through the 6 ohm, all right, and the current passing through R. Total current, 2,5. Current in the 6 ohm, 0,83. And then current in R, I don't know it, now I can find it. The current in R becomes 1,67 amps, almost there. So now I know the current in R is 1,67. And it makes sense now. If I was to add 1,67 current and 0,83 current, I'd get 2,5 amps because here it's divided, but it will come together as 2,5. So what do I know about R now? I know the current in R, 1,67. I know the voltage in R is definitely 5 volts. voltage in parallel. And I'm looking for R. I'm almost there. The resistance of R will now be equal to the voltage divided by the current. Let me be specific. Let me do this. Let me say the resistance of R there is equal to voltage in R and current in R. What is the voltage in R? It's 5 volts. What is the current in R? It's 1,67. So what would be the resistance of R for my 7 max? My answer is 3 ohms. That's my resistance of R, and my 7 max comes in. Again, family, this whole thing of knowing how parallel and series work is super important. So that's my answer. You can write this one down. If you have any question whatsoever, I'm here and I'm willing to answer your questions. I'm willing to answer your questions. Somebody sent a message, right? I didn't get the second part. By second part, I don't know what you're talking about, but I might as well just do everything again. You must familiarize yourself with how current works, how voltage works, and in what type of circumstance. Again, in a parallel circuit, the voltage is the same throughout the parallel resistors. The current will be different, but the voltage will be the same. Fine. And so the voltage in the 6 ohm there, the voltage in the R there, those voltages will be the same, pretty much. And then in essence now, if I find the voltage in 6 and voltage in R, I found the voltage in R and 6 combined, which is the voltage in parallel. I was able to get the voltage in the 1 ohm because it is connected in series, and the current that passes through is the total current in the circuit. So the voltage there will be 2,5 volts. The total voltage of the circuit when the switch is closed to 7,5. Fine. 7,5 there, voltage parallel plus 2,5 gives me voltage in parallel there, which is 5 volts. So that 5 volts belongs to the 6 ohm, that 5 volts belongs to R, that 5 volts belongs to their combination. Voltage does not change in a parallel arrangement. And now because I've got that, I can get the current now. And current, 6 ohm V over R, then I get 0,83 for current. But the current is, the total current is the current in the 6 and current in R. That gives me current in R as 1,67, resistance of R as the 3 ohm that you see in that particular context right there. So I'm pulling through on that one. So that's my answer on that. Okay, people are asking about 8,1 and 8,2. 8,2, let me start from 8,1. When the switch is open, here's the point. When the switch is open, there's no current, right? There's no current. Who is there? The voltmeter. Where? On the battery and on the switch V2. No current when the switch is open. Sharp. Now, what is the voltmeter V1 registering? 10 volts. That's the EMF. Everywhere, 10 volts. Why? There is no current. So the power source, which is your particular voltmeter, which is your particular battery, that power source has a maximum energy per column of charge of 10 volts. Everywhere, the maximum energy per column of charge is 10 volts. And that's how you define EMF, by the way. So effectively, when there's zero current, there is no, the voltmeter reading at the battery and the voltmeter reading at the switch will be the same. There is no current. Switch is open. 8,1. 8,2, 8,21 there. Close the switch. The switch is not an electrical device. It doesn't use electrical power, unlike the resistors. It doesn't. So therefore, the voltage is zero right there when the switch is closed. The current will not be zero, true, but the voltage will be zero when the switch is closed for V2. And that's how your answers look like, guys. All right, allow me to move on. We'll be okay on this one, okay? Allow me to move on. We'll be okay. Let me move on to the next question, 8,23. 8,23. 8,23. It says, define in words the term internal resistance. So internal resistance, you can write it this way. It is the opposition to the flow of charge within a cell. It is the opposition to the flow of charge within a cell. Okay, beautiful. Opposition to the flow of charge within a typical cell. That's what internal resistance is. And 8,24 says we need to calculate that one. So judging by what I know from the equation that I have, the EMF is equal to I and then R plus R. And Mina, for 3 marks, I'm looking for internal resistance. So I still remember my numbers there, that's okay. And then we can take it up from that perspective. Now, judging by what we're given that the EMF was 10. The total current in the circuit was 2,5, right? And big letter R, we pretty much don't know. And small letter R is what we're looking for. But big letter R, which is the total resistance in the circuit. And please, guys, remember, we had remember this, we had this, the 6 ohm, right? And then we did find R as 3 ohm, okay? I remember that one there. We found R as 3 ohm, right? And then we've got the 1 ohm resistor right there. So the total resistance in the circuit, big letter R, would be the combination of this particular parallel plus the bigger brother, that one. And because parallel here, there's just 2 of them, I can pretty much do the whole idea of saying PS, product, that's 6 times 3 over 6 plus 3 plus 1. Remember, when I say 6 times 3 over 6 plus 3, I'm getting the resistance of this parallel. Then I need to add that to this one, which is in series. So basically, that's what I'm doing. So I get the total resistance there, which is big letter R. And mathematically, this is 3 ohms. Fine. So now I'm looking for the rest is maths, 10, 2,5, big letter R, 2,5. Big letter R is 3 rather. It's 3 plus R. The rest becomes algebra. And then R, at the end of the day, I found it as 1 ohm. That's 8,2324. 1 ohm for R. 1 ohm. All right, write this down. I want to move on to something else. All right, I want to take this out. 8,3, we go. 8.3. Remember, we are learning. We are making sure we understand everything. We are pulling through and we're asking questions, and you're free to do. I see people are saying now they understand on the chat. Thank you so much. You guys will be okay. 8,3. Does the reading on the ammeter increase, decrease, or remain the same when resistor R is removed? Increase, decrease, or remain the same when resistor R is removed? Let's just go back a bit to the question. Right, if you were to remove resistor R, so this guy is gone, R is gone. What you have done is that you have removed a resistor in parallel. So you removed a resistor in parallel. So what is the implication? If you remove a resistor in parallel, number one, the total resistance of the circuit increases. It's very important to understand that. If you remove a resistor in parallel, the total resistance of the circuit increases. Let me give you logic. Now, before we removed R, before we removed him, remember that his value was 3 ohms. And when we did the total resistance, I think we found it also as 3 ohms. That was what you did. But if you remove R, if R is gone like this, now you're left with a 6 ohm and a 7 and a 1 ohm, and they're connected in parallel. So the total resistance becomes 7. Before then, when R was available in parallel, it was 3. So removing a resistor in parallel increases the total resistance. Fine. The implication is that current will decrease. That's what's happening. Because resistance and current are inversely proportional. You must understand resistance as opposition to the movement of current. Resistance. So the more the resistance, the less the current. So in the implication then for that question is increase, decrease, or remain the same. And my answer is decreases. So your answer is decreases. I'll come back to another question which stretches this part to 2 more points. I'm not going to tell you it now. I'm going to come back to it later on. Fine. So it decreases. Please remember that when you remove a resistor in parallel, it pretty much decreases, right? Let me take that out. Somebody's asking, where did I get the 1 for RT? The 1 for RT. No, RT, when, okay, I think if you're thinking about the resistors when they're connected, all of them together, the total resistance was not 1, it was 3. That was the total resistance. Remember, these guys gave me 2 ohms plus this one here, which is 1. At the end of the day, I get that. So I'm not sure what you're talking about. Are you talking about the small letter r? It was just a mathematical implication on the small letter r there. So I think it was like this. EMF is equal to I, big letter R plus small letter r. So that's my 10 right there. I think the total current in the circuit was 2,5. Big letter R was 3 plus this one here, which is that. And then this is becoming 7,5. I'm not doing the maths now. Plus 2,5 R as 10. It's algebra, guys. 2,5 is equal to 2,5 R. Divide by that. R is 1 ohm. That's the question that I was doing. Then that's where I got my small letter R. It's algebra, family. Guys, I really worry about your algebra, Nick, because the physics ended here. The rest is math. The physics ended right here. When you've substituted everything, the rest is just math. So let's get that thing clear up and nicely going. All right, let's go to our next one right there. Here's a question. It's a 2015 Eastern Cape paper. Please write the title down and we take it up from there. Somebody raise their hand. I want to be able to unmute. Go ahead.
So the total resistance, would it be still right if we were to say the total voltage over the total current?
Okay, the total resistance. Are you talking about before I remove R or while R is still available?
No, before you remove R.
Before I remove R. So the total resistance will be the total voltage over the total current. Yes, that's fine. That'll be okay. Yeah, that's pretty much okay. Okay, let's try another question altogether. It's the 2015 Eastern Cape Prelim Paper 1, and it's question number 9. I read in your hearing, there's a graph. Okay, trying to move the stuff away. Okay, let's move it maybe to the top. All right. Learners conduct an experiment as shown in the diagram below. All right. There's your diagram. The results obtained are shown in the graph below. Fine. The graph looks like it's a straight line, but it's decreasing. It's a straight line, but it's decreasing. I've got current on the y-axis and potential difference on the x-axis. 9,1. Use the graph to determine the following: the EMF of the battery. Okay, fine. Let's think. I said just now that the EMF will be available when the switch is open, and when the switch is open, the current is 0. It would be nice if we're looking at a diagram, but we're looking at a graph. So it's available when the switch is open, when the current is 0. Now look at this graph. When the current is 0, the voltage is 1,5. There. The x-intercept. Right there. In other words, when the current is the y value, this x-intercept tells me that y is equal to 0, which is my current. And what is the voltage when current is 0? The answer, 1,5. So just by looking at this graph and judging it, you can be able to tell that when the current is 0, the voltage potential difference will be 1,5 volts. So your answer for 9,11 is 1,5. Current 0, voltage 1,5. And when the current is 0, family, please keep in mind again and again that the voltage at the end of the day will be your EMF. And that's your answer. Fine. Let's go further. 9,12. Calculate the internal resistance of the battery without using this equation, okay, in your calculations. I'm fine with this. Let's begin. So my graph is similar to my first question that I did, I think. I and then V. My graph is similar. Oh, no. I'm going to do it the other way around now. Okay. Okay, let me quickly mute one of you here. Okay, one of you is unmuted. I want to make sure that I mute that. All right, I think this should be okay. I'm okay with this now. Let's move on. Okay, I was saying if you look at your graph, it's exactly like that, and I want to make sure that we understand what's going on. I'm looking for the internal resistance. I'm not going to use those formulas. This graph is decreasing. The gradient should be negative, and that's key. You see, if you were to find the resistance of this graph, its gradient, because it's negative, will be representative of the internal resistance of the battery. Keep in mind, the internal resistance of the battery always drops the voltage all the time. It always drops the EMF. So because of internal resistance of the battery, the EMF becomes smaller by all means. So then I'm clear then that at the end of the day, I'm looking for the internal resistance. I'm going to get the gradient. It's going to be negative, judging by the shape of the graph. And that particular negative gradient will be indicative of the internal resistance, right? Fine. But because I've got IV, remember, my resistance at the end of the day should be 1 over that particular gradient. Keep in mind what I said in the first question. Let me get the gradients. Okay, use first and last points, end points. I'll use the y-intercept and the x-intercept. So here I've got 0 and 1,8. That's for my y-intercept. I've got 1,5 and 0. That's for my x-intercept. I'm going to get the gradient, which will give me a negative number. I know change in I over change in V, y2 minus y1 over x2 minus x1. All right, there you are. And I'm good on that one. Okay, at the end of the day, then, this is what you're going to have. I end up having 0 minus 1,8. I see a hand. I'm going to attend to you now. And then also, that's going to be 1,5 minus 0, y2 minus y1. And the resistance and the gradient, rather, becomes negative 1,2, if I'm not mistaken, because I did this before. So that's gradient. But remember, I'm looking for the internal resistance. And because I get a negative gradient, it's indicative of the particular internal resistance. Fine. So then it becomes now 1 over 1,2. You don't need to put the negative there because I know that by virtue of that, I'm talking about the internal resistance, right? At the end of the day, guys, your particular, okay, let's do it this way. Did I do it? Let me do it this way so that I can show you before I do the shortcut version. So remember, I had said to you that if your graph is of current and voltage, Bradley, I see your hand, I'm gonna come to you. If your graph is of current and voltage, then your gradient of that particular graph would then, its reciprocal would be the resistance, right? That would be its reciprocal. And so if I do that and bring this guy down here, that internal resistance is 1 over 1,2. I'm not so sure what answer I get there. Should be 0,83. Let me check my calculator very quickly and see if I get that answer. Yes, 0,83 ohms. That will be the internal resistance right there. Let me quickly unmute you and we take it up from there. Go ahead.
All right, so I wanted to say I couldn't hear you, but I'm fine now.
Okay, good. That's fine. Let's go further on the next one. You can mute yourself in the meantime. There. Let me go to my next one. 9, I think the next one on the next page. Write this down quickly, family. Keep in mind again how to get the resistance, how to get the gradient, and all those kind of things, the relationship between every one of those particular terms that you're looking at. All right, let's keep going. I am good to go. All right, I'm successfully taking this out. I was waiting for other guys to finish. That's fine. Here's my next one. 9,2, it gets interesting. The resistance of the rheostat is now increased. So the resistance of the rheostat is now increased. Remember, the other name for rheostat is variable resistor. So we increase its resistance right there. Okay. And then it says now, how will this change the voltmeter reading? Right, increase, decrease, or remain the same? And explain your answer. Maybe let me take you back to the diagram so that you can see what's on the diagram. So this is your diagram. We have increased the resistance of the rheostat. Okay, how does that affect the voltmeter reading? And if you notice the diagram, the voltmeter is actually right there on that particular resistor there, the voltmeter reading. Let me explain. Increasing resistance, right? Increasing resistance. What it actually does is that it decreases current. So because there was an increase in the resistance, there will ultimately be a decrease in the current. Fine. And let's get this clear. For the same EMF, you see, EMF is always a constant, it doesn't change. And EMF is voltage external plus voltage internal, or lost volts. Or we pretty much know it as IR plus IR. Or we pretty much know it as I bracket R plus R. All these are the versions of EMF. Now, because you decreased the current, and how did I do that? I decreased current by increasing resistance. The rheostat resistance is increased. What will happen is that the decrease in the current will affect your lost volts, which is your internal resistance. So your lost volts, eventually, lost volts are also decreased. I usually like to say, whatever happens to current happens to lost volts because they are cousins. So decrease current, decrease lost volts. So once the lost volts are decreased, to keep the EMF constant, then the voltage external must increase. So in essence, the voltage external must definitely increase. And the question says, how will the voltmeter reading change? So in this case, again, listen up. You've increased the resistance. sharp. So what's the implication? Current decreases. Why? Because current and resistance are inversely proportional. Current has a cousin brother, lost volts. Whatever happens to current happens to lost volts. So the lost volts, which are voltage internal, they will also decrease. And when they decrease, the voltage external, to keep the EMF constant, must increase. So the answer for 9,21 is increases. The explanation is what I'm going to give from there on. So write it down, 9,21 increases. Let's explain it. Write the following. Number one, the resistance of the circuit increased. That's number one, point number one. Resistance of the circuit increased. Okay. Number two, the current will decrease. So that's my second point here. Current will decrease. Okay. Then on point number three, for the same change, or rather for the same EMF, the lost volts will decrease. For the same EMF, the lost volts will decrease. So whatever happens to current happens to lost volts as well. Okay, fine. And then finally, the voltage external will then also, in essence, increase. So that's basically what's going to happen. All right. That's what's happening. So let me take this out. That's 9,22. These questions come out a lot, and they're usually about 4 marks. So they'll ask you this one, then the explanation as well. So you must know that it comes out, the effect of increasing, decreasing, and all that. Let me go to 9,3 quickly. 4 identical cells. Oh, there they are. 9,3. 4 identical cells, each with an EMF of 1,5 and an internal resistance of 0,25 are connected in series. So the EMF of each cell 1,5 and an internal resistance of 0,25. So they put each in capital letters, are connected in series with each other, and the resistors as shown below. So there's my situation. It says here now on 9,31, write down the potential difference across the cells when the switch is open. So when the switch is open, that means I'm dealing with the EMF. And they want me to write down the potential difference across the cells when that switch is open. Each cell gives me 1,5. Okay, there are 4 of them. So therefore, the total EMF in those 4 cells is 6 volts. And that's your answer. So for 9,31, write down. There's a difference between calculating and writing down. So in this case, it's just a simple thing. Write down. So it's 6 volts. 1,5 volts here, plus another 1,5, plus another 1,5, plus another 1,5. There are 4 of them, and each gives me an EMF of 1,5. So that's your answer right there. 9,31, 6 volts. I'm on 9,32. When switch S is closed, so I close switch S, okay, the potential difference across the 4 ohm resistor is 2 volts. So let me get this right. We close the switch, and the potential difference across this particular resistor is 2 volts. And then calculate for 9,32A, calculate the current in the circuit. So I'm looking for the current in the circuit. And let's get this right. The current passing through the 4 ohm resistor is undivided. It's not divided at all. It will get divided between the 14 and RX, I agree. But right now, it is not divided. So if I get the current in the 4 ohm resistor, then I've found the total current in the circuit, the undivided current. Yes, it will divide. Let's say the current moves from positive to negative. There it is, current come through, passes through 4 ohm undivided, divides between 14 ohm and Rx. But when it passes through the 4 ohm, it's undivided. So if I get the current in the 4 ohm, I'm actually getting the total current in the circuit. And so the current in the 4 ohm at the end of the day is voltage over resistance. The voltage being 2, the resistance being 4, the current being 0.5 amps. So the total current in that circuit for 9,32A is 0.5 amps. Okay, write that one down. That's okay. Nine 9,32B. RX, guess what? 8 marks. Feel no fear. Feel no fear when you see 8 marks. Feel excitement because you're going to get all the 8 marks proper. So feel no fear whatsoever when you get this 8 marks question that you're looking at right there. Okay, RX, calculate. That's what I'm looking for. RX in this particular context. Allow me to move on this perspective. Now, we know the EMF. What is that? It is 6 volts, sharp. So let me write my information. EMF, I looking for you, 6 volts. I know you. R, small letter R. Keep this in mind. Each particular cell has an internal resistance of 0.25. So how many are there? 4. Each 0.25. So the internal resistance, the total internal resistance of these particular cells, in this case, because there are 4 of them, each giving 0.25, the total will be 1 ohm. 0.25 times 4. That's what I'm getting. Okay, all right, fine. I see that, right? I see that. And then now I know that the current total, here we go. Total current is 0.5 amps. That I know. Total current, 0.5 amps. The undivided current. Okay? I'm looking for Rx. And this is my information. Well, at least I know this guy. I just don't know Rx. Fine. Do some physics. EMF is equal to I, R plus R. Okay, right? EMF, 6. Total current in the circuit, right there, 0.5. Big letter R, I don't know it. Small letter r is 1. So in this case, it becomes 0.5 r plus 0.5, and that's 6. I'm doing some algebra. This one at the end of the day, okay, let me do some maths. This one at the end of the day, annotate this, is now 5.5 is equal to 0.5 r. So my total resistance in the entire circuit is 11 ohms. But who makes this 11 ohms? Who makes it? It's made from bigger brother 4 ohms and the twins. So this total resistance R is a result of the parallel combination, which I don't know, and the 4 ohm resistor. And so 11 is equal to R parallel plus 4. So now I know that the R parallel in combination is actually 7 ohms. So I'm good to go. Now, but how do you get this R parallel if you wanted to do it? There's 2 of them, PS. So the R parallel is basically, let me put this here so that we can pick it up from there. All right, so R parallel is basically PS, 14 multiplied by Rx over 14 plus Rx. R parallel, who are you? Let's bring it here. 7. 14 multiplied by Rx over 14 plus Rx. Cross multiply. 7. 14 plus Rx is now algebra family is equal to 14 Rx. Let's bring it elsewhere. Let's bring it elsewhere. Let's bring it here. It becomes 98 plus 7 Rx is equal to 14 Rx. 98 is equal to 7 Rx. I'm doing algebra. Rx is actually equal to 14 ohms. I get 8 marks. That's what Rx is equal to. 14 ohms, and I get my 8 marks. Talk to me if you're not struggling. Okay, someone is asking, so say, is it always the case that whenever you have the current that's undivided, it's always the total current in the circuit? My answer is yes. Undivided current is actually the total current in the circuit. It will divide itself amongst the parallel resistors, but in essence, that becomes your answer there. So that's a yes for me. So that's 9.32. Rx is 14 ohms. Rx is 14 ohms. Please write this one down and we take it up from there. So someone is asking, where is the 14 coming from? I divided 98 divided by 7, and it gives me 14. 98 divided by 7. Let's confirm that. Yeah, 14. So remember, I'm looking for Rx. That's what I'm looking for. 98 divided by 7, I get that. Somebody's got a hand, and I just want to make sure that I attend to that. Go ahead.
So I wanted to ask, would the total EMF formula be given in the data sheet?
Yes, this one is given. It's given. It's always given.
Okay, thank you.
Okay. All right. Let's move on. I'm taking this out quickly. Once you speak, guys, don't forget to mute yourself. Once you speak, don't forget to mute yourself. All right, I'm taking this out, and let me try another question all together. Okay, here's another question. It's a 2014 exemplar paper 1, and it's question number 9. 2014 exemplar paper 1, and it's question number 9. All right. In an experiment, learners use the circuit below to determine the internal resistance of a cell. Okay. That's my circuit. The circuit consists of an EMF of E and internal resistance of R. A voltmeter is placed across a variable resistor set to known values of R. The equation, okay, that's new. The equation is 1 over V is equal to R over ER plus 1 over E. So these learners use that equation. Okay, fine. Let's go on further. Then it says here, they obtain the graph below. Find 9,11. Write down the mathematical relationship for the slope of the graph. Okay, let's do some physics. Now, here's what I need you guys to see, right? The equation that we were dealing with, that were given in the previous slide, was 1 over V is equal to R over ER plus 1 over E. That's what we're given. Okay. And the question then says to us here, let's write down, it says write down a mathematical relationship for the slope. A mathematical relationship for the slope. The other name for slope is gradient, right? Judging by my graph, I have 1 over V as my y-axis and 1 over R as my x-axis. Okay, and here's my equation. Your graph is a straight line graph. And when dealing with the straight line graph, your basic equation is always y is equal to mx plus c. That's for a straight line graph. Y is equal to mx plus c. Now look at how interesting this gets. 1 over v is your y. Okay. 1 over r is your x. So let's relate what we have on the graph with the equation. I can rewrite this equation in this format. I can say 1 over v is equal to r over e multiplied by 1 over r plus 1 over e. I can do that. Follow my thinking. You know why I can do that? Because if I say r multiplied by 1, I get r. If I say e multiplied by r, I get er. So I just separated this, and I've got r over e plus 1 over r. That's what I have. And so the y value becomes 1 over v. The x value is 1 over r. Then this r over e is your m. And the 1 over e is your c. So the slope and the gradient, m, is actually r over e. And that's your answer. Let's go back. Let's go back. Relate what you have, your equation, to your graph. Who's the y-axis? 1 over v, y. Who's the x-axis? 1 over r, x. And then I'm going to break down this equation into an equation where I'm able to separate my y version and my x version. So I'm going to have this as 1 over v. That's okay. Checklist. I'm good on this guy. 1 over v. But I'm going to separate r over er as r over e multiplied by 1 over r. It's correct because I can always go back. I can always say r times 1, r. I can always say e times r, er. So I wanted to do that so that I can have this 1 over r, which is my x. My y, 1 over v, plus 1 over e. There you are. So in essence, now this r over e will stand for m. Mx plus c. Y is equal to mx plus c. Y, 1 over v, is equal to m r over e, x multiplied by m, x, then 1 over r plus c, 1 over e. So the gradient, the slope of this graph is r over e. That's what it is, r over e at the end of the day. Or check this out. If you don't want, you can do the traditional way, what we usually do. So gradient is change in y values, 1 over v, over change in x values, 1 over r. Then you do some math, which is 1 over v multiplied, then you invert this, r over v. So this is still applicable, r over v. So you can have it as your answer, m is equal to that, or m is equal to that. But why I prefer this one is because the further questions like 9,12 will ask for EMF, and I need to know this to get EMF, but this will also be correct for 9,11. Let's talk. Let's talk. And I've repeated. That's what you get. You convert this equation that you're given for a straight line, break it down into small little pieces, and it becomes, you break it down in such a way that you expose Y, you expose M, X, as well as C. That's how you can pick up the slope of the graph. Okay, I'm going further on this one. I'm going further on this one. EMF of the cell. Let me try EMF of the cell. I want to take this out. Let me give it a further 30 seconds. EMF of the cell. Nothing difficult, guys. We get excited when we see this question. We really get excited. All right? Really get excited when you see this question. Okay. This I'm taking out. I'm looking for the EMF of the cell. That's what I'm looking for. EMF of the cell, which is given by the letter E. Judging by what I have here, you see, you notice from the equation 1 over V is equal to R over E multiplied by 1 over R plus 1 over E, right there, okay? Like what you have in that context there. All right. Okay, let's keep going, guys. We're good. So 1 over V is equal to R over E multiplied by 1 over R plus 1 over E. We had said to ourselves that this will be your Y, this will be your M, okay, X, and your C. And I mean, I'm looking for the EMF. That's what I'm looking for. Fine. 1 over E is always the Y-intercept, this value. So this 1 over E is your C, and this is your Y-intercept. So I'm going to go to this graph here and pick out what this Y-intercept is. And I picked it out earlier. It's actually 0.65. So in other words, when X is 0, Y is 0.65. And I'm looking for E. So then 1 is equal to 0.65 multiplied by E. Then now I can divide by 0.65 to get that particular E. So at the end of the day, E is now equal to 1.54 volts. That's what E is equal to. So that's your answer for 9.12, EMF of the cell. Let's try 9.13 and see if we'll win. Internal resistance. Again, guys, if you don't understand something, please do ask me. I beg you. If you don't get something, do ask me. I beg you. But this is a very interesting question because it links up mathematical concepts together with physics concepts. And so it's very important that you get this right. Okay, let's go further on this one. I want to go to 9.13, where I'm calculating the internal resistance of the cell, small letter R. Internal resistance of the cell, small letter R. This I'm taking out now. So this is going. Internal resistance of the cell. Okay. Now, your slope, M, your slope, ne, is R over E, right? That's what we had already affirmed. We have E sharp. We're looking for R. We don't know. And we also don't know gradient. But I can get gradient from the graph itself. When I get that gradient, then I can get my small letter R, which is internal resistance of this cell. And so how would I get the gradient? I just need 2 points. So I'm going to pick, let me pick this one. Let me pick the one whereby I've got my Y-intercept. So I'm picking when X is 0 and Y is 0.65. Let me try and see if I can pick another coordinate. Yes, I can. Let's see. I can pick this one when X is 2. Guys, you can pick any. As long as they're correct, you get the same answer, right? X is 2, and then Y here should be 1.3. So that's 2 and then 1.3. So I picked this other point there. You guys can check this out in your spare time. And I want to get gradient now. So gradient here is now y2 1,3 0,65 over 2 minus 0 right there. I get my gradient is 0,325. That's my slope. But I'm looking for R. 0,325. Okay, is equal to R. I don't know R. 1,54 from the previous question, EMF. And then the rest is just math. R is actually 0,5 ohms. There you are. Pretty much understandable. Talk to me, family. Talk to me. Talk to me if you don't understand so that you can get this right. 9,12, somebody's asking me to repeat that, so not a problem. In instance with 9,12, right? So all your simple doing, right, is to be able to calculate or rather look from a graph. Okay, guys, write this down, then I can explain 9,12. While I attend to one person who's got their hand raised up, and I want to unmute you. Go ahead.
Hi, sir.
Hi.
Sir, can I ask for the gradient when you are calculating 9.1.3 internal resistance, why didn't you substitute 1 over one over your points, like for instance 0.65, say 1 over 0.65?
Okay, it's because I'm not having a graph of voltage or rather of current versus voltage. You only do that if your graph is current versus voltage. Remember,
Thank you,
this
sir.
is just 1 over V and 1 over R. So I think you're mixing two graphs here. There's the graph of current over voltage, where if I got that particular gradient, I was able then to say to myself, that gradient is reciprocal, will give me my resistance. But again, also keep in mind that you're already given an equation and you're given the letters of that equation. R being your internal resistance, E being your EMF, and M being your gradient. And you can simply get your gradient by using these 2 points that you have there. You can get your gradient by using these 2 points that you have there. And I got that gradient, and then I said to myself, this gradient is M, checklist. I've got E, checklist. I'm looking for R, and I found R right here. So you only use that in context of what you have. And in this case, you do not have I over V. You've got 1 over V and 1 over R. Okay, that would be my answer. Yeah, that would be my answer. All right, beautiful. Okay, let's go further on that one. Somebody's asking me to repeat 9,12. Guys, when you've got a graph, mathematics topic is analytical geometry. When you've got a straight line graph, this particular coordinate here is always your y-intercept, which from a graph will be mx plus c. So c is the y-coordinate of the y-intercept. And remember, the x-coordinate will be 0. And in this case, the y-coordinate is 0.65. That's your answer right there. And you guys must be able to interpret a typical graph. And this is how you do it. Don't worry, I'm going to teach you. Now, if you were to ask me, where did I get these coordinates from? Now, if I go here, 1, and then this one is 1,5. The difference between 1 and 1,5 is 0,5. And how many squares do I have here? How many squares do I have here? I got 10 squares. So divide that between 1,0 and 1,5. I have 10 squares. It's a graph paper. So basically like that. So now you've got 0,5 divided by 10. There you are. And then this gives me 0,05. So every single square is 0,05. So if I come here, let me use a different color pen. If I come here, this is 1. Then this one now will be, I'll add 0,05. Then this one will be 1,1, right? Then 1,15, 1,2, right? 1,25, 1,3. That's how I was able to tell you that this coordinate will be 1,34y. So that's what you do. Get the difference between the two numbers, 1 and 1,5. then divide by the number of squares, then each square becomes the answer of that division. So you move from 1, 0, 8, 0,05. Now I'm on 1,15, right? Then 1, 1, then 1, then 1,05, sorry, then 1,1, then 1,15, then 1,2, 1,25, 1,3. That's how you do it. That's how you calculate the values there in that particular square. All right, let's move on quickly. Let's move on this one and see how far we can go. I'm on the next one. There's a family. Let's try and move on quickly on that. Okay, here we go. It's a story, an interesting story right there. Right, somebody asked and said, say, on these types of questions, are we always given the same equation? No, you're not. You just need to be able to see your graph, and then from there on, make it into y is equal to mx plus c, see your y value in that equation, and your x value, and then extrapolate your gradient, your m, and your c. So no, it's not going to be the same equation. 9,2 quickly, guys. Probably that should be my last question here. 9,2, we're almost close to our end time. In the electrical circuit shown below, the battery has an EMF of 6 volts and an internal resistance of 1 ohm. The total external resistance of the circuit is 9 ohm. Please note this very important information. So internal resistance 1 ohm, total external resistance 9 ohm, EMF of the battery 6 volts. 9,21. Calculate the current R1, the current in R1 when the switch is closed. Okay, beautiful. Now, when the switch is closed, obviously we've got the current passing through R1, and that current passing through R1 is not divided. It's not. Current is divided between R2 and R3. So the current passing through R1 is not divided. Appropriate equation. EMF, I have you. Current, the I is the total current in the circuit. R is the total resistance in the external circuit. Small letter r is your internal resistance. EMF, 6. Total current in the circuit, I don't know it. Total resistance in the external circuit, when you're combining R2, R3, and R1, is actually 9 ohm. Then internal resistance, 1. The rest is maths. I multiplied by 10 is equal to 6. So I, at the end of the day, you're going to divide yourself. 6 divided by that particular 10 is going to be 0,6 amps. That's your I. Write that one down. So the current passing through R1 is the total current in the circuit, which is this from the equation. I is 0,6 amps. Fine. Let's go further on the next one. I'm on 9,22. I'm on 9,22, all right? But let's read the information that we're given about 9,22, and let's clear this up here. 10 more seconds here. We pulled through from that level. Okay, 9,22. This is going. There you are, gone. Sharp. The power, first time we're hearing this today, the power dissipated in R1 is 1,8 watts. The resistor of R3 is 4 times the resistor of R2. They even gave you. R3 is 4 times R2. 5 marks, calculate the resistor of resistor R2. I gather my information. Power in R1. So the power dissipated in R1 is 1,8 watts. Okay, that's power. You know, power has a lot of equations. You should see this. And see, the one I'm going to pick is this one, and I'll tell you why right now. You see, power, I have it as 1,8. Current passing through R1, I found it now as 0,6 squared. And so I can get the resistance of R1. I can. And the resistance of R1 at the end of the day, when you do your maths properly, is equal to 5 ohms. Fine. So I know the resistance here, 5 ohms. But I'm looking for the resistance of R2. Okay, let's keep going. Now the total resistance of the circuit is 9 ohms. That's what we're told. So the total resistance of this external circuit, and who's that? Is when I combine the twins and the bigger brother, I get 9. So the resistance of the parallel and resistance of R1 added together give you 9. Maths. Resistance of parallel I don't know, but R1 I know you, 5. So the resistance of the parallel combined together is now 4 ohms. But I'm looking for R2. We're given the information that R3 is 4 times R2. Okay, here's what I suggest. Just say to yourself, let R2 be equal to X. It becomes a bit easier to think about it. Let R2 be equal to X. So in other words, R3 becomes equal to 4X. That's what R3 is equal to. But the resistance parallel here in this case is obviously 4 ohm. And how do I get this resisted parallel? I would have said PS, where I would have said R2 multiplied by R3 over R2 plus R3. That's what I would have said to get the resistance parallel. The resistance parallel is 4 ohms. Okay. R2 is X. Let R2 be X. R3 is 4X. Okay. R2 is X and R3 is 4X. Let's do algebra. So when I do algebra now, I will notice then that 4 is equal to 4x squared, okay, over 5x, x plus 4x. 20x algebra is equal to 4x squared. I'm looking for x, so I'll divide both sides by 4x, and therefore x is 5. And what is x? R2. So the resistance of R2, which is X, is 5 ohms. That's what the question was asking. And that becomes your answer. 5 ohms. So in this case again, remember family, you're using the information about power to get your resistance of R1. But the total resistance of the circuit external is 9 ohm. That 9 ohm is inclusive of what I add from parallel there and what I add in R1. Then I get the resistance parallel as 4 ohm. But I'm given some information that R3 is 4 times R2. So let R2 be X. Then how would I have gotten R parallel? And I'm using PS again. Product there over sum there. The rest is maths. Therefore, R2 is 5X. Talk to me. Not difficult. Understandable. We are going to make it. We'll get this thing right. Okay, we'll pull through on this one here. So that's your R2. I want 9,3, a hair dryer. So finish this up here. Let's go to 9,3, a hair dryer. All right, so if there are no questions on this one, I can quickly move to 9,3. All right, I'm about to take this out. Just finish this up quickly. All right, gone. 9,3. A hair dryer operates at a potential difference of 240 volts and a current of 9,5 amps. So V of that hair dryer is 240. Current of that hair dryer is 9,5 amps. It takes a learner, that's the time, 12 minutes to operate or to completely dry her hair. Eskom charges energy usage at R1.47. So that's the tariff, or that's the unit charge. It's R1.47. It says calculate the cost of operating the hair dryer for 12 minutes. So we need the cost of operating the hairdryer. Now, there are many ways of doing this, but I prefer you actually think about it this way. Cost is power that the hairdryer is using multiplied by the time taken while the hairdryer is in operation, multiplied by the unit price. That's my preference. So let's get the power of the hairdryer. My information about the hairdryer is voltage and current. And there's information, or rather a formula that says power is voltage times current, 240 multiplied here by 9,5. I get an answer here like 2,280 watts. That's my power. But remember, when you're calculating power made, or rather the cost of electricity, you convert the power into kilowatts because your unit charge is 1 kilowatt hour. So that's very important to remember that. So you convert that into kilowatts. So how do I convert watts into kilowatts? Divide by 1,000, 2,28 kilowatts. So my power is 2,28 kilowatts. So that's my power. Multiplied by the time. The time is 12 minutes. But your unit price or your unit is measured in kilowatt hour. So we've converted watts into kilowatts. Now we need to make sure that our time is in hours, kilowatt hour. But here it's in minutes. So how do you make hours? How do you make minutes into hours? Divide by 60. So the time is 12 multiplied by 60, converting the time into hours, kilowatt hour. The unit price is R1.47 per unit. And so your maths for the cost is 67 cents or Rand 0.67. And that becomes your answer for the cost of electricity. All right. So that becomes your answer pretty much, and write this down. So we've done pretty much almost 2 hours of our lesson. You guys have been wonderful. You've asked questions. I hope you guys have understood. You can always check more questions, try to do them. Watch this again, rewatch it, share it, let someone else know, and go back to it over and over again as you need to. So it's very important then at the end of the day to pretty much do our best for the final exam. We're not going to panic. Preparedness is key. When we are prepared, we are more settled. When we are prepared, we are more in control. We don't want to be anxious in the exam. We don't want to be fearful in the exam. We don't want to scrap over and over again and just try to hold this and hold that, and it doesn't look like we know what we're doing. So the time for preparation is now. And it's a good thing that you guys came here, you watched, you learned, and that's basically it. I'm going to take this out now and maybe just give one more announcement and end our beautiful lesson here. So I'm going to take this out. This is out now, and then we take it out from there. Speaking of preparedness, you can see what's happening. I'm going to be having these massive revision programs that are going to be happening 2, 3, 4 November. That's for maths. 9, 10, 11 November, that's for physical science. 3 days each subject, 8 hours a day, face-to-face with me. You can imagine the amount of stuff that I can say and do in 8 hours when I am with you per day for 3 days. It's going to be massive. High flyer questions, time management in an exam, focusing on challenging topics, exam tips and all those kind of things. So if you're interested, you can just DM me, and I think my number is right there, 0739748498. You can check my Instagram page, Mr. X Maths Science, and also my Facebook page as well. So I'll be posting more information on that one. But otherwise, guys, let's do what we need to do. And I wish you all the best in your preparedness for the final examination. I'm going to stop and end our lesson right now. See you again soon enough on our next lesson if need be, and we take it up from there.